Okay, in my last video, we talked about counting using the permutations and the combinations and also the fundamental counting rule. In this video, I want to take it one step further and apply those counting techniques to probability problems. So in this video, I want to focus on just two main problems, and we'll use those two problems as sort of a framework in terms of how to determine when to use which method and how to apply them. So, for example, let's say, what is the probability of being dealt a hand of cards from a standard 52 card deck that contains 4 aces? Okay, so a 5-card hand, 4 of those cards have to be aces. Now, what type of counting process is this? Well, there's a few things that we have to identify here. So there's only one of each card in the deck. So there's 52 cards in the deck, one of each. So there's no repeats. And when we choose those 5 cards, once you have 5 cards in your hand, if you shuffle those 5 cards into a different order, it's still the same 5 cards. So order does not matter. Order doesn't matter. And if there's no repeats and order doesn't matter, and we're choosing a small group of 5 from a larger group of 52, that is a combination problem. Or combinations, choosing a small group from a larger group, no repeats, order does not matter. Okay, so we're definitely going to take a combination approach to counting. So how do we calculate probabilities? Remember, the essence of calculating probabilities is counting. Always counting. We have to count 2 things. How many ways can your event happen? So our event is being dealt a hand of 5 cards that contains 4 aces. That's our event. 4 aces in our hand. We also have to calculate how many different ways the process. So let me erase this green here and here. Let's say containing 4 aces, that is our event. Let's call that event A. And the procedure is being dealt a hand of 5 cards. So we need to know how many different ways you could be dealt a hand of 5 cards, and we need to know how many different ways can a hand contain 4 aces. So it's always counting, and we have to count 2 things. How many ways can our event happen? How many ways can our experiment happen? Okay, so what do we need to count? Oh, we just went over that. So our definition of probability, the number of hands that contain 4 aces, and the total number of 5-card hands. So these are the 2 things we need to count. And we've already talked about this. The counting rule is the combination rule. Okay. So we're choosing 5 objects from a group of 52. Order doesn't matter, and repeats cannot happen. So again, this is a combination. And we have a formula for this. We could use our we could use a calculator, we could use paper and pencil, or we could use Desmos. Okay, and then finally, once the counting is done, then we divide those 2 numbers and we'll have the probability. Okay, so let's go through the process. Let's see what we could do with this. So let's start with this. How many total hands are there of 5 cards? How many different groups of 5 are there from the group of 52? All right, so we know this is a combination problem. Out of 52 objects, we are choosing 5 of them. Okay, so we can apply the combination formula. So that's n factorial divided by n minus r factorial, n minus r factorial times r factorial. Okay, 52 minus 5 is 47, and the numbers 1 through 47 on the bottom will cancel off the 1 through 47 on top, leaving us with 52 times 51 times 50 times 49 times 48 divided by 5 times 4 times 3 times 2 times 1. And once we pop this into the calculator, you'll see 2,598,960 possible poker hands. So out of those 2,598,960, how many of them contain 4 aces? Well, there's 5 cards, so you think about there's like five available slots. 4 of them are already taken by those 4 aces. So there's 1 available slot left. So how many hands contain 4 aces? Well, the first card is an ace. The second card is an ace. The third card is an ace. The fourth card is an ace. And the 5th card, you have options. So how many options do you have here? We're starting with a 52 card deck. Take away those 4 aces and you're left with 48 cards left. So for that last card, there's only one way this could happen. Only one way for these 4 cards to be aces, and it's for the hand to contain all 4 aces in the deck. Let's just go back one more slide. So we have 52 minus the 4 aces. That leaves us 48. And so there are 48 options for that last card. So there are 48 5-card hands that contain 4 aces. Now now that we've counted the number of hands that contain 4 aces. That's 48. We've counted the total number of 5-card hands. That's the 2,598,960. Okay, so we've counted these 2 things. The counting is done. The last step is the probability. We divide these 2 numbers. And if you pop this into a calculator, you will get approximately 0.00185%, a very low probability. Now, whether or not you know how to play card games, we don't need to know any rules or the structure of any games, but just conceptually, the idea that why does one hand beat another hand? Why is one hand stronger than another hand? For example, 4 of a kind beats a hand with 5 cards of the same suit, called a flush. Now, why does 4 of a kind beat a flush? Well, the probability is lower. So the lower the probability, the stronger the hand. Okay, so that does it for that example. One more. So let's say we have this combination lock here, and it has the numbers 1 through 40 on it. Well, it has 40 numbers, 0 through 39, not 1 through 40, 0 through 39. So I have 40 numbers. Now find the probability that the combination to unlock it consists of these 3 numbers. It's a 1, a 2, and a 3 in some order. So the combination to open the lock could be 1, 2, 3. It could be 3, 1, 2. It could be 2, 3, 1, and so on. So any 2, 3, 1. Any order of the numbers 1, 2, 3. So of all possible combinations, how many contain the numbers 1, 2, and 3. So we're going to have to count, again, count two things. How many different combinations are possible, and we're going to have to count how many combinations contain specifically the numbers 1, 2, and 3. And once we count those two things, we divide them. Again, counting first, division second, and that's how probability works. What counting rule do we apply here? Well, we're given in the problem, numbers can't be repeated. So we have no repeats. And if you put the numbers into the lock in the wrong order, it's not going to open. So we know order definitely matters. When you're unlocking a combination lock, order definitely matters. And so with no repeats, order matters, and we're choosing a small group from a larger group. So here's the R, here's the N. This is a permutation. Which I think is interesting because the name combination lock is a little bit misleading. It's actually not a combination lock, it's a permutation lock. Because the idea of combinations is that order doesn't matter. Okay, so we'll call it a combination lock because that's what they're called, but it's not entirely mathematically accurate. All right, so again, we're choosing 3 numbers out of 40. Order matters, repeats are not possible, so we're dealing with a permutation, and we have a permutation formula that we could apply now. Once we know what to do, now it's time to actually do it. Okay, so like I said, our N is 40, the R is 3, and we can apply the permutation formula, which is N permutation R equals N factorial divided by N minus R factorial. Okay, so N factorial is 40 factorial, N minus R, 40 minus 3 is 37, so we have 40. So the numbers 1 through 37 on the bottom cancel the numbers 1 through 37 on the top, leaving the 38, the 39, and the 40. And we pop that into a calculator. 40 times 39 times 38 gives us 59,280 possible combinations on our permutation lock. I know I said I was going to call it a combination lock, but I changed my mind. Okay, so now that the counting's done, oh, well, actually, no, the counting's not done. So we've counted how many total possible combinations there are. Now I need to know how many combinations contain exactly the numbers 1, 2, and 3. Started listing them on an earlier slide. Now, with such a small number like this, we could start listing them out until we've listed them all. 1, 2, 3, 1, 3, 2. Those are the only ways you could start with a 1. What about starting with a 2? 2, 1, 3, or 2, 3, 1. Okay, those are the only ways you could start with a 2. And let's say it starts with a 3. 3, 1, 2, 3, 2, 1. So it looks like there are 6 ways the combination could possess the numbers 1, 2, and 3. If you don't like counting by listing, we can apply the fundamental counting rule. And the fundamental counting rule says there are n factorial different ways to arrange n distinct objects. Remember, distinct means different. So if we have 3 different objects, there are 3 factorial. 3 factorial different ways to arrange them. And 3 factorial is 3 times 2 times 1, which is 6, the same 6 that we got by listing. Okay, so for probability, the number of combinations that contain a 1, a 2, or a 3, we've got 6 for that. The total possible combinations, 59,280. And we'll pop that into the calculator. 6 divided by 59,280 gives us roughly 0.01%, or 1/100th of 1%, which is about a 1 in 10,000 chance. Not exactly 1 in 10,000, but close. Okay, so that about does it. I mean, the last video was the meat and potatoes of this topic, the counting. That's where all the work is done. Once the counting is done, the calculating the probability is that part is easy. Take those two numbers that you just counted and divide them. Okay, so that about does it for this set of notes. After this, we'll move on to the next big topic. After this is probability distributions. So that'll be the topic of the next video. Okay, that's it for now.